Okay, let's get started. Today we're going to talk about large language models, and specifically we're going to do a brief introduction. So we're not going to go into the details of the math of how large language models are implemented, but we're going to discuss how we're going to discuss primarily two things. The first thing is how the text that you use to interact with large language models gets converted into a numerical representation for the neural network. And the second thing we're going to talk about is emergent properties okay, forget that. The second part of what we're going to talk about is how these models are trained. All right, let's start. So all of you have used ChatGPT before. So ChatGPT is a class, it's one of a class of models called large language models. And the name is actually really well put. So the model is large, meaning it has a huge number of parameters. So recall from our first lecture that neural networks have parameters, and these parameters are essentially like these matrices, right, that the model will learn from the training data. And it'll essentially take these matrices, multiply it by the input matrix, and end up in the end with an output vector. So it has a ton of parameters. ChatGPT has over 100 billion parameters, and GPT-4 is estimated to have about 1 trillion parameters. So these are really, really massive models that you need gigantic GPUs to run on. Not all large language models are that large, but they're typically in the billions, well into the billions of parameters. They're a language model, meaning that they learn like written text, right? Including typically English, but also other languages. And in fact, these large language models have are trained on such massive data sets that they often have the ability to translate between multiple different languages, because the data set will contain a lot of English, but also other languages, and actually gets the ability to translate between these languages. It's something we'll talk about later called emergent behaviors. And it's a model because it's a neural network, it's a machine learning model. And as you can see here, we have a diagram of the inputs and outputs. The input is just your text input, like the prompt that you give ChatGPT. And the output is of two forms. One is the text output, the response from ChatGPT. And the second is a numeric representation of this output. So what this is that internally, all neural networks will represent all data as numbers. And so it needs to represent this text as numbers also. And so this numeric representation, we're going to get into the details here about why we want to convert text into vectors, and how this can be useful, how it's useful semantically also. So we know that we interface with large language models through text, and neural networks are entirely comprised of numbers. So how do we translate between text and numbers? And this is really, really important. This is the number one thing we're going to learn today. So for those of you who just came in, this is an intro session to large language models. We're going to talk about two things. The first is how to convert text into numbers, and back into from numbers into text, because you interface with ChatGPT and other large language models through text. But neural networks all use like a bunch of matrices. So how do you convert between the two? And the second thing we're going to talk about is how these models are trained. Okay, let's move on. So the first step in converting text into numbers is a process called tokenization. What tokenization means is taking sentences and breaking them up into these things called tokens. So tokens are like components of, let's say, a sentence. And you can tokenize at a number of different levels. So during tokenization, you need to do a number of things. One is that you need to remove the white space. So in English sentences, we have a space between every word. But what we want to do instead is we want to take out the white space and make a list of tokens instead, right? And this is called preprocessing, where we take the input text and then convert it into another form that we're later going to use. We also want to add a couple of special characters. One is you see this tag like S, right? What this means is the start of the document. And you also have the n/s. which represents the end of the document. So the first S will be inserted at the beginning of the document, and the second S will be inserted at the end of the document. These aren't part of the document, but they tell the model where the document starts and stops. And the reason for this is that when you're training the model doesn't really know like what the start of the document is, and so you add these special characters to denote the start and end of the document. And on the right, we have an example of tokenization. We have the sentence, "We love NLP," and we tokenize it into 4 tokens. The first is the word "we," second is the word "love," the third is the word "NLP," and the fourth is the exclamation point. So there are several different levels of tokenization, and there are really 3 levels that are mainly in use. One is at the character level. So what this is we take the sentence and we just take it character by character and remove all the white space. So as you can see, every token is just a single letter. At the second level, we have word level tokenization. We have the 4 tokens in this case. This is tokenizing in the period. And finally, we have what's called subword level tokenization. We have this, and then is, and then token, and then ising, right? So notice that this is quite similar to word level, except we've now broken up words to some extent, especially in tokenizing. Before it was a single word, now it's 2 tokens, the token and the ising. And so just to gain an intuition for this, what do you guys think is the like pros and cons of each level of tokenization? And which one do you think is most commonly used, especially in large language models like ChatGPT?
Yeah, I was wondering like if the subword level it might be computationally expensive, like determining where a subword is in a word. So most likely I think it's word level that it's broken down and it's tokenized to.
Let's pretend that computers are infinitely fast. Which level would you like to tokenize that?
Probably subword.
Why?
It breaks down a word into like what it's looking at and then the action. Like tokenizing, it will understand what token is, and then ising is like an action.
Yeah, that's exactly the correct intuition. So subword level is the level of tokenization that's the best. And actually, I haven't looked into the exact details of the algorithm, but subword level tokenization is actually computationally efficient enough that we are actually able to use it, and it is being used in ChatGPT, Bard, and all the other major large language models today. So subword level tokenization is best because we can break words up semantically. So typically people have this intuition that a word is a token, but actually if you think about it, words are composed of multiple parts. If I have the word like univariate, uni tells me 1. And so even like parts of the word actually give me a lot of information. And in this case, tokenizing is really 2 words. It's the token part and the ising, which represents that it's an action, right? And so if you break up words into subparts through subword level tokenization, you can actually extract a lot of the semantics for the model. So is it really that easy? It's actually pretty tricky to tokenize sometimes because of special characters and other like semantics, right? For example, we have conjunctions. Like we have the word let's, for example, right? Which means let us. So how do we tokenize this? And this semantically means let us, right? And maybe a more informal fashion. But what is this? How do we tokenize this, right? Should we tokenize the word, the subword let, and then the apostrophe s? Should we tokenize the apostrophe and the other parts of the word separately? Or should we tokenize it entirely as a single word? And this is like somewhat subjective, right? And no matter what kind of like framework you use, there's always like some subjectivity at play where like you could argue like one of them is better than the other, right? So for example, let's start with the second one. The second one is tokenizing on punctuation, right? So every special character is getting its own token, whereas the third one, the bottom one, is tokenizing on white space. So it's splitting everything on white spaces, which we saw before is not ideal because it doesn't break up the words into more semantic units, right? And then the first one is actually pretty nice because you can see let, right, and then us as like two separate tokens. And we do have like is and not like tokenized separately. So this is nice because the word isn't is really comprised of is and not. And so it is tokenizing these separately. Although maybe one thing that could be improved is it could break up the word tokenize into token and eyes. So tokenization actually has like a number of steps. And we discussed a few of the really important ones today. Notably, we want it to be at the subword level, and we need to take into account special characters. And at the subword level, there's a couple of interesting properties. One is that it can handle what are called out-of-vocabulary words. So what does out-of-vocabulary mean? When you train these models on a data set, there will be a ton of words in them. And some words actually will be in the, like most of the words in the English dictionary will be in the data set. But what if you give it some word you made up, right? Or that hasn't seen in the data set for some reason. Potentially, it can understand what you mean if it's being subword level tokenized, because it can understand parts of the word you're saying, right? Just as a random example, if I say the word like treeifying, right? This isn't a real word, but if I were to say that, it probably means something to the extent of like making something into a tree or something like that. And we know this because we know the word tree, and then the part like ifying is like in general like common English for like turning something into. And so subword level tokenization algorithm can handle this for us. Even though the model has never seen the word treeifying before, it can kind of deduce that what this means. And so if you like make up words to ChatGPT, it should be able to like have some deduction abilities for what you mean, or if you make a typo or things of that nature. And in fact, subword level tokenization dates back a couple of decades in history. The subword level tokenization algorithm used by ChatGPT is called byte pair encoding. And it was actually not originally invented for large language models. This was invented multiple decades ago. It was invented for data compression. And only later did OpenAI decide to use it for large language models. And it was invented for data compression because it turns out that this byte pair encoding algorithm has some nice like information theory properties. And so by using this, by applying byte pair encoding, you actually get like an output that means the same thing as the original input, but has a smaller, occupies a smaller disk space. And on the right, you can see an example of tokenization for GPT, right? And so you can see that GPT-3, even though it's like a word, is actually tokenized into multiple different characters because it's an acronym, right? And at the same time, words are typically either like captured in full, for example, many in words, or they're broken up. For example, you see tokenization. We have the token as a single token in red, and then ization as another token in blue. And these colors, I don't think they actually mean anything. I think they just like denote the that every like color is a different token. So like genera is a different token from ativ, right? Or genera is a different token from ativ, and which is a different token from pre, and so on. So you can actually play around with this yourself. You can look up GPT tokenization. I think they have an open source library called TikToken for this. So it's kind of fun to play around with to see like how your text is being broken up before it's being passed into ChatGPT. So in practice, you don't want to write your own tokenization algorithm because there's a lot of edge cases that we talked about before. For example, like you can split on white space, but then like how do you handle special characters, right? How do you handle like conjunctions? How do you handle the word like isn't, right? Or like aren't. A lot of this has been studied by natural language processing researchers and solved to a large extent in open source frameworks and libraries. For example, Spacy. So Spacy is a very popular natural language processing library that can use in Python to perform common natural language processing tasks. For example, tokenization. So here what we're doing is we're importing the library. We're loading a, it looks like a medium model, and we're processing this text, right? We are learning NLP using Spacey into a document. And then what we're doing is we're looking at the document and getting every token, right? And we're printing out what the text of the token is. And this token class has other attributes to it too. I don't know off the top of my head, but if you install Spacey, you can play around with it on your own and really take a look at what a lot of these like standard NLP approaches have come up with. And it's a really useful tool in practice also. So this is useful for educational purposes as well as for real production systems. And there's a bunch of other implementations. For example, OpenAI has tick token. So here's how you would use tick token, right? You import it, and then you get the encoding for a particular model, and then run the encode function. And then you eventually get like a bunch of numbers. So these numbers actually represent which token it is. So you can imagine like if we have like every token associated with a number. For example, I might have the word like cat as a token, and that might be number 1, right? And then dog is number 2, and then tree is number 3, and so on until I've like enumerated every single token in my data set, right? And that's what's done here. So it looks like we have the 15,496th token, and right after that is a 2,055th token, and so on. And these numbers are really quite arbitrary. You can define them however you'd like, as long as they're consistent. Yeah, and you can see what's being tokenized here, right? Hello, community, exclamation mark. So it looks like hello is a token, then community, and then exclamation mark, right? Corresponding to these 3 numbers below. So hello would be 15,000 or so, community would be around 2,000, and then exclamation mark would be around 5,000. And here's just yet another example at the bottom. Okay, so we've run tokenization on our text, and we've come a long way. We've broken it up from like these huge sentences into these like little parts of speech, little bits that actually have some semantic meaning. But we still need to represent this as vectors so that we can pass it to the neural network. Because neural networks, remember, operate only on numbers, and they still don't understand text, even if they're semantic tokens. So how do we do this? We do this through something called embeddings. So what an embedding is, it's the vector that represents a word or a token. Strictly speaking, it should be token, right? A vector that represents a token. But you can intuit this as representing a word. And there's 2 types of embeddings. There's static embeddings, where like if you give me a token, I can give you an embedding, right? So it's just like imagine a hash map, right? We have the number for each token, and if you do a hash map lookup, you can get the vector for that corresponding token. Contextual embeddings are quite different. You're not able to actually get the embedding just by knowing what token it is. Instead, you have to give an example of a sentence in which it's being used. And we'll see why that's useful later. And contextual embeddings are really important. They have much better accuracy than static embeddings. We'll look at exactly why very soon. And contextual embeddings are what are used in large language models. Static embeddings were invented a little bit ago, and they're really important for earlier research. And we've developed contextual embeddings today that build on top of static embeddings and perform better. So we have our input text, remember, from the data set that we've tokenized. And then what we're going to do is we're going to pass into what's called an encoder. Now, an encoder is a part of a large language model. Large language models typically have 2 parts, or 2 main like high-level parts, an encoder and decoder. The encoder will take the text and convert it to this like vector, and the decoder will take this vector and convert it into text. So you might have a prompt for ChatGPT that you pass to the large language model. So this whole thing right here, right, spanning from this green box to the blue box will be the large language model. ChatGPT will convert it into like this context vector, which represents everything you said. And that context vector will be passed to the decoder part that generates a bunch of output text in response to your prompt. Okay, so what are static embeddings? So static embeddings have been in earlier research, and they really show up in this one important paper called Word2Vec. So if you look up Word2Vec, it is really a paper that explains some semantic relationships along static embeddings. And the idea of this is that every word in the English dictionary will get its own vector. So for example, I just made this up, but we can take the word dog and convert it to like this vector with like 5 elements, right? Or this array, 0.92, 0.28, and so on. And these are just arbitrary. But the idea is that we don't want them to be completely arbitrary because we want them to encode relationships between words. So here's an example. Let's say we're looking at 4 words in the English dictionary: king, queen, man, woman. These words have relationships between each other, right? A king and a queen is pretty similar to a man and a woman. And so that's what's represented by this dashed line here. Their distance is the same, right? So the difference between a king and a queen is essentially that a king is male and a queen is female. And so you can see that the relationship is shown on this graph here, right? They're the same distance away with the same direction away also. And so you can actually perform a little bit of math here, right? What is king minus man plus woman? We have king minus man, right? And then plus woman. What should we get? We should get queen, right? And so this is also represented in vector math too. If you recall vectors, you can represent them and you can draw vectors in 2 dimensions. And if you perform this vector math, right, king minus queen plus woman, you'll end up at this queen vector. So you can imagine these as distances from the origin, right? So a vector pointing from the origin to man, origin to woman, and so on. And then if you perform this vector math, you'll end up with the vector of queen. And there's this really, really important concept within embeddings called cosine similarity. So why is it called cosine similarity? The reason it's called cosine similarity is because we want to compare how similar 2 vectors are. And the way we do it is by considering how far apart they are in terms of their angle in between. So cosine similarity is going to be a score between I think this is wrong. I think it should be -1 and 1. But essentially, cosine similarity is going to take the angle in between the vectors. So imagine I have vector A and I have vector B, right? So my arms are the vectors. And if you consider the angle in between, that's going to tell you how similar the vectors are. So if my arms are opposite each other, this means maximum dissimilarity, right? They're as far apart as humanly possible. And if they're the same vector, then they're pointing in the same direction. And if the angle's close, they're pretty similar. If the angle's very far apart, they're quite different. And so you can see the math here, which is that the cosine of the angle in between, theta is the angle in between the vectors, is equal to the dot product of the first vector and the second vector divided by their magnitudes. So why are we dividing by their magnitudes? It's because we want a score between -1 and 1. This is wrong. It should be -1 and 1.
I think it's saying the vectors that are closer to 180, they're similar relation but opposite. So it says city country versus country city. So it's still technically related.
It is related, but in the opposite way. So the negative sign is important because it tells you the opposite relationship, right? It's quite different from 0. 0 means they're not similar at all. So I guess you can say a negative score is similar, but it is opposite. So yeah, you can see a couple of examples here. For example, France and Italy are pretty similar, right? They're both countries. And so the angle between them is pretty small. And if we take the cosine of that angle, you get a pretty large number, or very close to 1. And ball and crocodile are very different, right? They represent completely different concepts. And so theta will be around 90 degrees. They'll be perpendicular. And so that'll mean they don't really have a relationship between each other. And finally, let's see. France minus Paris, Rome and Italy. It looks like they flipped the order of things here. So this is a country to city, and this one's a city to country. So they're essentially the opposite order. And so these vectors, right, will be opposite of each other. And remember that the reason we divide by the lengths is to get something between -1 and 1. So if we don't divide by the lengths, right, we might have a vector that's way longer than the other. And this can screw up our similarity score because we might have a vector that just happens to be super long. And so it has a high similarity with a bunch of vectors, even though it's not actually that similar. Does this make sense? Okay. Yeah, This is a really important concept, and it's actually not too hard to understand. I think sometimes it's overcomplicated. Cosine similarity is just taking the cosine of the angle in between two vectors. And the cosine of the angle in between the two vectors is the similarity between those two vectors. And the way you compute it is you don't actually find the angle. You just use this mathematical relation, which is that the cosine of the angle is equal to the dot product between the two vectors divided by their magnitudes. So we can run through an example, right? What's the cosine similarity between these two vectors? So when you actually perform these computations, you're going to perform them on like real numbers, and you'll like probably write a program to do this for you. But let's go through a conceptual example, right? We have the vectors 2, 7, and 1 as our first vector, and 8, 2, and 8 as our second vector. So we'll take the dot product, right, between the two. What is a dot product? The dot product means you take the first two values, multiply them, take the second two values, multiply them, and take the next two values, multiply them, and add those all up, right? So you do element y's multiplication, and then add up your results. So you have 2 times 8 plus 7 times 2 plus 1 times 8. And you get 38. And then what we need to do is we need to convert this to something between -1 and 1, right? So to convert it between -1 and 1, we'll take the magnitudes of the vectors, which is their lengths, right? So if you imagine these vectors as like in a plane, or in this case, like a three-dimensional space, right? They have a certain length. What is that length? To get the length, we'll use the Pythagorean theorem, right? Between the origin and that point in the in 3D space. So what is that? This is square root of 2 squared plus 7 squared plus 1 squared, which is square root of 54. And we do the same thing for the second vector to get its length. And so if we take 38 and divide by these two lengths, we end up with a score of about 0.45. So these are not that similar, but have a little bit of similarity. Does this computation make sense? Okay, great. Okay, so static embeddings are quite nice. They do encode semantics between words, right? They encode relationships, as we saw in the king, queen, man, woman example. But they also have a couple of problems. The main problem is that words have multiple meanings. And so look at this. We have two example sentences. The first is, I will wire you $1,000 from my bank account. And the second sentence is, he was so wired, he paced the river bank for an hour. Now, because static embeddings assign a vector to every word, it basically does this like hash map lookup, right? Where it looks up like the word and then gets the vector corresponding to that word. That means that wire will have the same vector in both sentences, and bank will also have the same vector in both sentences, because every word gets a single vector. But these words, even though they're the same, mean different things, right? Wire in the first sentence is talking about a financial wiring, right? Wiring money. Whereas wire in the second sentence means like a state of mind, right? It's talking about a person. So even though these are the same word, they have two completely different meanings. And they're not related to each other at all. And same goes for bank, right? In the first sentence, the word bank means a financial bank. Whereas in the second sentence, the word bank means river bank. Again, two completely different concepts, even though they're the same word. But static embeddings conflate the two, because static embeddings only assign one vector to every word. So this is the problem. When we speak English, we know what we're talking about because of the context of the conversation. So in the first example, if I say, I will wire you $1,000 from my bank account, all of you know that I'm not talking about wired as in a state of mind, and I'm certainly not talking about a riverbank. And the way you know is because I'm talking about financial terms. I say $1,000, and the word wire in conjunction with bank and account tells you that I'm talking about a financial setting. Whereas in the second sentence, you can tell that when I say he, I'm referring to a person, and so I'm talking about a state of mind, as well as when I say river, I'm talking about the bank of the river, right? And so language is very context dependent. The same word can have different meanings in different contexts. And so we need to develop a version of embeddings that is not the same no matter what context, but rather depends on the context. And this is exactly what large language models do. So large language models use contextual embeddings. What are contextual embeddings? So this is exactly what we just discussed. you don't want to look at words as just words that like have a single vector, right? A single meaning. Words are pretty multidimensional. They can mean a number of different things depending on the context. And so we want to use the entire sentence as a context for a word. And this is why, like, if you ask me a word, I actually can't tell you its exact definition, right? I have to ask you, like, can you use it in a sentence? Or, like, which version of the word you mean? Because words have multiple definitions. And so large language models use contextual embeddings. That's why, like, they're able to respond so effectively. Because when you give them a prompt, this prompt is going to have the whole context, right? If you say, I want to wire $1,000 from my bank account, it has the context of $1,000 as a financial term, as well as bank account and so on. So these context clues really help guide it as far as like to understand your intent. So let's go back a bit and review our earlier diagram. So I hope this makes a little bit more sense, especially the bottom right corner. We take in text input, generate text output using an LLM, and we also generate a numeric representation of the text useful for other systems. And these are the vectors, right? These context vectors are really, really useful, not only for the large language model internally, but also for things like search systems. For example, let's say I'm implementing like a search engine, right? And I want to have the search engine be what's called a semantic search engine. Not only should I include terms, right, like keyword search, like if I search for, Mars, then it'll like, literally search for the word Mars. But if I search for Mars, it should, like, let's say there's nothing that there is on Mars. It should also give me results for like Pluto, right? Or like, let's say Venus, right? Even though these, like letter-wise, Mars and Venus are completely different, they're referring to similar concepts. They're referring to planets. And so they're gonna have similar vectors. And so what you can do is you can take all of these vectors generated by the large language model, and you can basically find the one with the largest dot product, right? Or cosine similarity. And the one with the largest cosine similarity is essentially what you want to what you're searching for. Those are going to be your search results. And so you can use this numeric representation, these embedding vectors, for a lot of different purposes, including search and so on. You can even do this for images. You can convert images into vectors, like essentially describing what they are, and search along those images, like describing using text. And so these embedding vectors are super useful, both within the LLM and outside the LLM. Okay, now we're going to move on to the second part of today, and that's going to be talking about training. These large language models take in text and they generate output text, and we've discussed how to convert the text into numbers through tokenization and through embeddings. But how do you train the model, right? You have a data set, you've done all this pre-processing, how do you actually train it? Now, these large language models are actually pretty complicated, and they're trained in multiple stages. So the first stage is called self-supervised learning. The second is called instruction tuning. And the final stage is called reinforcement learning from human feedback, also abbreviated as RLHF. The first stage, self-supervised learning, is where we basically take a data set, right? We call this a corpus, typically. And the way we get this corpus is we basically like grab the like all the data we can get our hands on the internet, right? We just like get a bunch of bots and crawlers and spiders and whatnot, and basically like download like as much of the web as we can, typically like at least terabytes, sometimes maybe a petabyte even. And what we do is we do that, we're going to pre-process these, we're going to pre-process the data set. So what we do is we're going to take a sentence, like you can either take the red pill or the blue pill, right? And we're going to split it up. We're going to start with like part of the sentence. You can either take the red pill and then guess what word comes next. The next word is or, which we know from the data set, right? And so we'll split it up. This is the input we're going to give the large language model, and the output we want it to generate is the word or, right? And then we can do this a ton of times, because within even just a single sentence, you can split it up so many different ways. You can either take the red pill or, and then you can either take the red pill or, and then the next word should be the. You can either take the red pill or the, and the next word should be blue. And you can either take the red pill or the blue, and the next word should be pill, right? And so as humans, it's pretty easy to do some of this autocomplete. Some of it because I'm sure you are familiar with the movie. But even if you hadn't watched the movie or hadn't heard of this reference, you could still probably intuitively like guess after the word the, right? You can either take the red pill or the, because blue is essentially the opposite of red, right? And then if I say you can either take the red pill or the blue, we're talking about pills, so it's probably another pill. And so this is the intuition that we want our large language models to also understand. And so we essentially take this left-hand side as all of the x's. Remember, like all neural networks will take an input x and convert it to an output y. So this is the input, the left-hand side, and the output will be the right-hand side. And we don't need to like have a human manually curate these because they're present within the data. Like literally just by having a sentence, you can split it up into a bunch of different into a bunch of different pairs of this form. And the first part of your pair is going to be the input, and the second part of your pair is going to be the output. And you feed these all to the model, and this model will learn through backpropagation, as we discussed in the first lecture, right? And through backpropagation, it's going to update its weights, and by updating its weights, it's going to become a better model, and like over time, it'll become like a pretty decent based large language model. And let's say you do this, right? And let's say you like spend tons of money, right? Like these are really, really expensive because you have to train them on GPUs, and GPUs like use a ton of energy and are like really expensive to make in the first place. So like let's say you spend like $10 million and train on like 10,000 GPUs. So a question for you is, what's your output large language model? Do you get like the final stage of ChatGPT? If so, why? And if not, also why? So one way to think about this is like, as a human, is the only thing you use to understand text just like guessing the next word. So like this is probably not sufficient, right? Yeah.
Isn't like the next step to be working from both directions, like determine like what's the end of the sentence as well as like the beginning?
I guess you could do that. I don't think it's quite as important as the first part of like going left to right, because like left to right is our most natural way of prediction in human terms. Like if I were to ask you, right, how to like predict a sentence going backwards, for example, like you could do it, but like it'll like be a lot harder and probably not quite as useful. So it's like more natural for humans to go forwards, and in this case, we're going to focus on going forwards also. Yeah, so you don't actually end up with like your final like ChatGPT, the kind of large language model that you want. What you need to do is first a couple of other stages. So one of the problems of self-supervised learning, this is called self-supervised learning. Can anyone tell me why it's called self-supervised? So remember from our first discussion that supervised learning is where you create a data set and you manually label like this is a cat, this is a dog, and so on. Whereas unsupervised learning, you don't have to do that. Like the data is inherent, like the features are inherent in the data. So like if you have like a bunch of dots here and a bunch of dots here and a bunch of dots here, you can like use certain algorithms to like classify the dots without a human like labeling what cluster they're in. Why do you think this model is called self-supervised? Yeah.
It could score its output itself. It doesn't need like a given label in the data.
So because it generates a label, right?
Mm-hmm.
It generates a label itself. So it supervises itself. It generates a label because it's present in the data. You can take the red pill and then the next word is or, so it can generate that as the label for this input. And it can do that for every single label. So it supervises itself, and that's why it's called self-supervised learning. So yeah, there's a couple of limitations of just doing self-supervised learning. This is super important. This might be like this is more than 90% of the training of ChatGPT, but it's not sufficient. So if I ask, what is the capital of Italy? What do you expect is the output of this at this stage? What do you think is like in the data set of questions like, what is the capital of Italy? Like one answer is like the actual answer, right? But what could it also possibly generate?
It could just like, it could be biased towards like whichever like country got more of. So it could say like the capital of Italy is Washington DC or something really crazy.
I think it wouldn't in this case because of the next token prediction task. Because if you say like, what is the capital of Italy, in the training data, it won't have Washington, D.C. like right next to it. And so won't have learned that, yeah.
It might have another sentence.
Yeah, it might have another question, right? So what if you ask ChatGPT like, what is the capital of Italy? And then it responds to you, what is the capital of France? What is the capital of Spain? What is the capital of Belgium? This might like work really well from the self-supervised learning context. Like it is generating like very plausible sounding English that continues like the pattern that you started with. But this isn't what we want, right? We want to answer the user's question. And so this is the problem with only doing self-supervised learning. You need a lot of self-supervised learning. It teaches the model how to speak proper English or another language, but it's not sufficient because it'll essentially just copy like the distribution of the training data. It'll just copy the patterns it's already seen before, even if those aren't the patterns that you want. You want to elicit the response that helps the person using it the most. So we need something called instruction tuning. What is instruction tuning? So the idea of instruction tuning is that currently like the model has like learned a whole ton of stuff from a gigantic data set, and it's seen a bunch of different perspectives from like a whole bunch of sources, right? So for example, you might ask the large language model like, hey, what should I do for chest opening? And it has like a bunch of different personalities, like all within the model. So it has the like genius Magnus Carlsen response, right? It'll tell you like what Magnus Carlsen's like openings are because they're like published on the internet and it's learned those. And then it'll also tell you the Reddit troll response that gets you 2-move checkmated. So there's probably like some like really high scoring like Reddit comment, right? Of someone who's like, hey, like move this pawn up and that pawn up, and like you'll have a 90% chance of winning every game. And that's the 2-move checkmate, right? And probably you want the first response and not the second response, even if you see more of the second response. So there might not be that many Magnus Carlsens, and there might be a ton of Reddit trolls, but you still want the first response. And so what we do is this thing called instruction tuning, where we do what's called fine tuning. And fine tuning is basically like a smaller version of training. Previously, we did training on like terabytes of data to learn the language very comprehensively. And now what we're doing is we're learning on like a smaller tasks, right? We're learning finer grained details, right? So there's a couple of examples here. One is like, let's read it together. Here's a goal, get cool sleep on summer days. How do you accomplish this goal, right? And it gives the model a number of options. Keep stack of pillowcases in fridge and keep stack of pillowcases in oven. Now, it might have learned from Reddit or the internet like a whole bunch of troll responses, and they would say like keep stack of pillowcases in the oven, right? If we just use self-supervised learning, we might not get a good response. So like the model actually learns like a fair bit of sarcasm just from like human responses. It's learned that from the training data. We want to elicit the useful response, and so we'll have like a human labeled data keep stack of pillowcases in the fridge. So previously we had self-supervised learning. We generated labels based on the pattern of tokens in the data. And now we're actually bringing a human into the picture by like having them generate like true labels because we want the model to be useful, right? And not necessarily exhibit some of the personalities we saw previously. And same here, right? Let's do translation between English and Spanish. We have the English sentence and we wanted to generate the output sentence. And since we have this input-output pair, we can run backpropagation and update the weights in the model. And there's a whole bunch of different tasks, such as sentiment analysis. Sentiment analysis is basically when you take a sentence and analyze its sentiment, meaning like, is it a positive sentence? Is it a negative sentence? Like, is the person speaking happy or mad, right? That sort of thing. Co-reference resolution. It's not super important like exactly what these tasks are because you can always look them up. There's a whole bunch of different tasks that you can train the model on that'll like essentially update its weights, and therefore like once you get a new task, like it'll let's see. Yeah, well, like once you get a new task, right? Because you typically like ask ChatGPT like whatever you find useful, not necessarily something it's already seen before. And so when you ask it, like it should be able to deduce like what you want. Right? So if you fine tune it on a bunch of tasks, given its history of self-supervised learning, it should be able to give you a good response. So that's the second stage after self-supervised learning, instruction tuning. This is the second stage. And we have this third and final stage called reinforcement learning from human feedback. And this is that part where sometimes if you ask ChatGPT, like, how do I make cocaine? It'll say like, sorry, I can't help you with that, right? How do we get the model to deny unsafe requests? And the way we do it is through this technique called reinforcement learning from human feedback. So there is a safety concern with large language models, which is like, you can learn like all of the training data, but like some of the training data is a whole bunch of like really like cruel and bad stuff. And you don't want like the model to teach people like how to make weapons and things like that. So how do we prevent it from ever like saying stuff about like how to make weapons to kill people? We do it through reinforcement learning from human feedback. So reinforcement learning is its own subfield of machine learning, and it basically has to do with maximizing reward. And so like reinforcement learning typically takes place in an environment like traditionally video games, where like you can take actions and maximize reward. So reinforcement learning will typically like train an algorithm using a neural network to like beat a video game and play it better than humans, right? And it's also using robotics to like take actions like, hey, move like in this direction until you like find a human, help the human, and so on. But reinforcement learning is actually applied to large language models in order to do this, in order to perform this alignment, which is like making the model safe and like basically like behaving in a manner that we expect it to. So this diagram is from OpenAI. It's from, I think, the webpage where they introduced ChatGPT. And you can see that basically they're training what's called a reward model, which is basically, it's just taking like a response, like a prompt and a response, and it's assigning a score to every response. It's saying like, hey, this is like your question, right? This is an answer you like gave me. This answer is either good or bad, and it gives you like a numerical score. And the higher the score, the better the response is. And basically, it'll use reinforcement learning, which is a type of machine learning that operates on scores in order to maximize that score. We'll have a couple of ML Mondays on reinforcement learning either later this semester or next semester. So keep an eye out for those. And so we're not going to talk about reinforcement learning today, but it is a really useful subfield of machine learning. And specifically, it uses a reinforcement learning algorithm called PPO, which is proximal policy optimization. This is a really nice reinforcement learning algorithm. It's used in ChatGPT. It also was used to beat world champions at a game called Dota 2, which is a little bit like another game called League of Legends, if you guys have heard of that. It's just like a very like popular video game. And it's pretty complex, and it's like pretty amazing that machines are able to beat humans at it. Great. I'm not going to go too deep into reinforcement learning, but essentially, OpenAI like spent a lot of time studying reinforcement learning on video games, and then they looked at large language models and were able to apply it really effectively. Basically, the way reinforcement learning is applied to large language models is that the model will generate like a number of responses, right? So like, for example, let's say you're doing chess, right? And you're asking it like, what is the best opening? And it has like a Magnus Carlsen opening, and it also has a Reddit opening. So like you want Magnus Carlsen over the Reddit troll. So a human, what they will do is they will rank the responses, and they'll rank them from best to worst. So OpenAI just actually like outsourced like a bunch of like ranking collection. So they like hired people overseas essentially to like rank responses from the large language model, and the ones that are ranked at the highest will be like the ones with the most score, and will be through reinforcement learning what the model prefers. And so sometimes it's like hard to tell like whether a response is like just good or bad, right? Like two responses might like both be pretty good, but if you put them side by side, it's oftentimes easier to see like which one is better. And so that's why like ranking is used, and reinforcement learning can operate on the score generated from ranking. And a little bit more intuition on why we use reinforcement learning, even though this is like a text environment rather than a video game, is that standard training is what's called distribution matching. So we have a distribution of the data, and we essentially like memorize that distribution. Like this is like the next word that comes, right? But what we actually want is what's called mode seeking, which is where like we elicit like the version that's better than the other. So here, right, you can look at distribution matching as like sometimes generating answers towards this peak and sometimes generating answers towards this peak of like where the y-axis is probability, right? And like it might be the case that this peak is really bad and we actually never want to generate that at all. So we want to take like this peak instead, right? So that's what mode seeking is. Like instead of like generating this 50% of the time and this 50% of the time, it's going to always generate like the better one. Right? So that's what we wanted to learn. We want it to be very decisive. So here is this is a really realistic illustration of large language models and their stages of training. The first stage is unsupervised learning. That's where we have like the model predict the next token, right, or next word that comes after all the words you gave it. And this is like a really ugly monster because it has just like memorized all of like, it memorized a lot of like knowledge, but also memorized a ton of like sarcasm and like flame bait responses, right? A lot of trolling and so on. And so it's like this kind of ugly thing. It's also memorized like, you know, if you ask me a question, maybe I should just like give you a list of questions, which can be like really annoying. So it's memorized a whole bunch of like really annoying things that we don't want it to do. And the next stage after supervised fine tuning is like, we basically get rid of a lot of those like troll responses and other parts that we don't like. And it's a little bit nicer than the monster part, right? A little bit nicer than if we just use unsupervised learning. And then like the final like cherry on top is reinforcement learning from human feedback. So human feedback is like ranking the responses, and reinforcement learning is algorithm used to like generate responses close towards like the top of those rankings. And you can see that like, this is this like smiley face, right? That's hiding like this huge monster in the background. So if you interacted with like ChatGPT in its unsupervised form, it won't be, oh, by the way, unsupervised learning means the same thing in this case as self-supervised learning. Not necessarily in general, but in this case, the terms are interchangeable. So yeah, back to reinforcement learning from human feedback. This is really nice. Whenever you interact with ChatGPT, like it's generally like really happy, right? And like really friendly and wants to help you. And that's because like humans have went on and like labeled a whole bunch of like happy responses and supportive responses at like towards the top. And so now it generates answers like that are very, very close to that. Even if like previously in this monster form, it generated a whole bunch of like sarcasm. Now, it can still like generate sarcasm if you ask it to. Like it can like, this smiley face can like bring back some memories from, you know, its history, its past. And it turns out that like when we train the model all the way to the end, there's some abilities that it picks up that we don't expect it to. So we didn't like tell the model to do this. We didn't necessarily like fine tune it on this, but it's like able to do it. Right? For example, like to write poems that rhyme. You might think like, wait, like when humans think about poems, like think about phonetics, right? And they're like, hey, like cat rhymes with like bat, and so like if I want to write a poem, like this is how it might rhyme. But like machines don't really understand phonetics. It just has a bunch of these like texts and like these vectors, right? And they don't necessarily like have that much phonetic information. It might not be able to like pronounce things that rhyme. But actually like ChatGPT is able to write poems that rhyme. Just because it's seen so much data on words that rhyme that it knows like what kind of goes together. And the same thing between translation between languages. It's seen like so much text in like English that it really understands English, and it's seen so much text in Spanish that it's able to translate into Spanish and like associate words between each other. It's able to write code that compiles because it's scraped so many like public open source repositories of like well-written code, and it can like write code that can like, for example, like if you want to like make a snake game, you can ask it like, hey, write a snake game in like HTML, CSS. And like, I've tried this before actually. And like, I copy and pasted the code in the browser and like, it worked like out of the box. Like, it was really amazing. This is an example of like when ChatGPT was first released, someone was able to get it to behave as a Linux terminal. So they basically told it like, I want you to act as a Linux terminal, right? And like, here, like I'm gonna give you a bunch of commands. And just act as like a Linux terminal. And quite literally did. See, it's like giving it commands, and it's like behaving as if it's a Linux terminal. So here it's saying like, make a file called test.py and put print hello world in it, right? And then please execute using Python. And it looks like it's executing using Python, but actually it's not doing any of this. What it's doing is it's like pretending that it's a Linux terminal. It's like a human role-playing a Linux terminal. It's not actually executing anything. And so like this is really, really amazing Because like nowhere, probably nowhere like in the like we didn't expect it to like become a Linux terminal, but it kind of did because it's seen so many examples of Linux commands on the internet that it's just like able to do this. And this only happens in large language models, very, very large language models, where it's seen so much data that's able to do this. So small language models like, won't be able to do this. Very large language models like ChatGPT are able to do this. Except, well, I think they thought it was unsafe, so you're not able to do this anymore. It'll say like, I'm not a Linux terminal. Because they did some like reinforcement learning from human feedback to prevent you from doing this anymore. So we covered a lot today. We covered first tokenization, taking a data set of a whole bunch of like text and converting it into these words, and more accurately into tokens that are typically at the subword level and encode like semantics of those words. And tokenization also deals with things like special characters, including apostrophes, exclamation marks, right? These have semantic meanings, and they need to be considered in conjunction with text. We talked about embeddings, which is where we take words, tokens, to be more accurate, and convert them into a bunch of vectors. And specifically, we care a lot about contextual embeddings, where we consider words like in a context of a broader sentence, because this tells us like what the word, for example, bank means. If I have a sentence talking about finance, we know that it's a financial bank rather than a river bank. Then we talked about self-supervised learning, which is where you break up the data set into like chunks where you can like continue a sentence, and like you have the input of like the first several words of the sentence, and then the output of the next word of the sentence, and you have the model predict the next word in a whole bunch of those pairs. Then we talk about instruction tuning, which is where you basically want to elicit like the good parts, right? As well as reinforcement learning from human feedback, where humans rank the responses, and a reinforcement learning algorithm like generates responses towards like the top. And finally, we talked about immersion abilities. These kind of abilities that we didn't expect the model to be able to do, but it was able to do just because it's seen so much like data. It's seen such massive amounts of data that it's able to like emulate things that we didn't expect. And this can be really useful for us. So that wraps up today's lecture. And the next lecture will be a deeper dive into how this model works. So we talked today about like how's the text represented, how's it trained, and this is all like at a pretty high level, right? Super important, but at a high level. Next time we're going to talk about the internals of the model. Like what is the architecture, right? Because it's not quite like as simple as a multi-layer perceptron or a simple like feed-forward neural network where which we talked about like the first time, right? It's not just like a layer of neurons, then the next layer of neurons, and so on, right? There's this thing called a transformer architecture, right? And transformers are like a really like huge innovation in machine learning that's been responsible for creating large language models that work really well. And they're introduced in a paper called Attention is All You Need. Attention is a mechanism within the transformer architecture, and this is like one of the landmark papers. This paper was published in about 2017, I think, and it was published by, I think, Google Research. And they came out with the transformer architecture. They were working on some large language models, but like OpenAI caught wind, and like they just made like a way larger one. And now OpenAI is the one that's known for their large language models, more so than Google. But it's really interesting. Like now, like everyone's like working with transformers. It's spawned a lot of like innovation, right? Within machine learning, we've seen like huge like improvements and like leaps and bounds over the past like even just like 5 years, right? And it's really exciting to see like what's going to happen in the next 5 and to come. So yeah, that wraps up today's lecture. We're perfectly on time for 1 hour. And thank you everyone for coming.